For 6.2 day 2, we're really just going to pick up where we left off. We're going to solve a differential equation with power series, but we're going to find out that we can arrive at two different power series solutions. What we did before is we made a real quick assumption that we could have y was equal to sigma, going from n equals 0 to infinity. And our power series would be c sub n times x to the n. Y prime, taking a derivative, we said that that first constant, which would be c sub 0 times x to the 0, take the derivative of that, that disappears, and we adjust our counter accordingly to go from n equals 1 using our power rule for a derivative. This is c sub n times x to the n minus 1. Taking one further derivative, you're going to see we pretty much do the exact same thing. We're going to lose a counter, lose that first term expressed from sigma. If n equals 1, my very first term in this series would be x to the 0. It's a constant. Take the derivative of it. It disappears. We have n equals 2 all the way up to infinity. Here's c sub n times n minus 1. But now we drop our power down to n minus 2. We're going to substitute that into this differential equation here. We're going to have 4 times this n equals 2 all the way up to infinity of c sub n times n minus 1 times x to the n minus 2. But then we're going to say plus y, so we'll have plus sigma, where we have n equals 0 up to infinity of c sub n x to the n, and set this equal to 0. Now, of course, what we're going to do at this point is re-index. As I look at my first series, I have x to the n minus 2. So, to make a little adjustment, we're going to say let's let k equal n minus 2. You're going to see that just adding a 2 then, n itself would be k plus 2. And I'm going to revisit this sigma here. I'm going to bring the 4 inside now. But if n is equal to 2, plug that into our re-indexing. K is equal to n minus 2. 2 minus 2 is 0. So I'll have k equals 0. We'll still be going up towards infinity. If k is equal to n minus 2, n is equal to k plus 2. So I'll have c sub k plus 2. My n here would be k plus 2. N minus 1, well, that would be k plus 1. Could even go to this statement in red, add a 1 to both sides, and see that. But notice that my power of x, it was n minus 2. I'm revisiting that, I'm calling that k. In a very similar way, we're going to revisit this other series, and this is even way simpler. K is simply equal to n. We just very quickly readjust. K equals 0 up to infinity. This is c sub k, x to the k power. Set that equal to 0. We're better off in the sense that our series now are in terms of x to the k. And going even a step further, what you're going to see is quite nicely, we also have the same counter. So unlike what we were doing in our first lesson, we're not going to have to begin to pick off a number of terms from one of the sigma, generating a number of k values until our sigmas would have the same starting k. They do, as is, k is equal to 0. So that helps considerably. Let's just write this as 1 sigma then. And making a quick adjustment, we'd have 4 c sub k plus 2 times k plus 2 times k plus 1 Tell you what, I'm also going to simultaneously factor an x out from all of this. And very nicely we have this equal to 0. Well, my goodness, if this is really equal to 0, what you're going to see is this coefficient out in front of x sub k should be headed towards 0. So I'm going to really just write what I have in the brackets here. 4 c sub k plus 2 times k plus 2 times k plus 1 plus c sub k, set that equal to 0. Solving for c sub k plus 2 is not that difficult. You can see we're going to subtract a c sub k and then also divide by 4, k plus 2, and also k plus 1. Okay, what you're probably going to notice very, very quickly is that unlike what we did before, we don't have, these c sub terms out in front of our sigma, so we won't immediately have some information regarding them. However, what I want you to notice is I'm going to let k equal 0. If k is equal to 0, I would have c sub 2, and then of course we would have this equaling negative c sub 0. Down below, if k is equal to 0, you'd have a 2 times a 1 times a 4, and that simply is an 8. Now look, if I were to let k equal 1, I'd have c sub 3, and this would be negative c sub 1. Down in this denominator of, and when I'm referring to this, we could just take a look at these coefficients that I set equal to 0 and solved. I'm just going to keep plugging in different k values to generate a c sub 2, c sub 3, and so forth. If you let k equal 1 down below, I believe you'd get 24, because 1 plus 2 is 3, 3 times 4 is 12, 1 plus 1 is 2, so sure enough, take a look at this. Now, what I hope is immediately apparent is the fact that our k equals 1 is actually not going to lead us to a statement about c sub 0, but c sub 1. Let's continue to adjust this. If k is equal to 2, go back up to what I've highlighted in yellow. You'd get c sub 4 would equal negative c sub 2. And down below we have 2 plus 2 is 4, 4 times 4 is 16, and then 2 plus 1 is 3, so we'd have 48. Now, if you look at the k equals 0, you could see that c sub 2 is actually negative c sub 0 over 8. And we're going to use that information to help us out even right now. So, making this substitution from up above about c sub 2 when k is equal to 0, we can see that just writing this off separately, we'd have negative 1 over 48, but c sub 2 is negative c sub 0 all over 8. That becomes a positive c sub 0. 8 times 48 is 384. Well, notice what's happening. We're back to a c sub 0. What happens if we get k equals 3? Well, if k is equal to 3, we'd find c sub 5. And we'd have negative c sub 3 all over, well, 3 plus 5 is, 3 plus 2 is 5, 5 times 4 is 20, and 3 plus 1 is 4, so we have an 80 down here. So this is negative 1 over 80 times c sub 3, but notice what c sub 3 is. Look up above, we get negative c sub 1 all over 24. Now again, you're going to notice that the negative 1 times negative c sub 1 is going to cancel 80 times 24 is 1,920. So we're growing quite a bit, but notice more to the point what is occurring. We're alternating in each successive term between having a c sub 0 or a c sub 1. More to the point, I hope what's going to become apparent is that this series expansion is going to be dependent on, then, two different constants, namely c sub 0 and c sub 1. So, look, even if we were to just take a momentary pause here, and we could generate even more if we would so choose. But look, if I were to just go back and say, look, from n equals 0 to sigma of c sub n x to the n, this is what my solution would be. We'd say, well, this would be c sub 0 plus c sub 1 x plus c sub 2 x squared plus c sub 3 x cubed plus c sub 4 x to the 4th plus c sub 5 x to the 5th, and so on. But now look what we have just found. We began getting information about c sub 2. So when I see c sub 2, I'm going to replace it with a minus c sub 0 all over 8. With c sub 3, I saw that that was negative c sub 1 all over 24. With c sub 4, we saw it was a positive c sub 0 over 384. With c sub 5, we saw it was positive c sub 1 all over 1,920. And evidently this is going to be continuing on. Now, hopefully, again, it's very, very evident that what's happening for this solution of y is that we could find two distinct different series solutions that could work. What we're getting at is this. We could take a look at the family between c sub 0 and c sub 1. So if c sub 0 is equal to 1 and c sub 1 was equal to 0, then we'd see that y would equal, well, let's see, c sub 0 would be a 1. And then we'd say minus, well, c sub 1 was 0, so actually you're going to see everywhere where there's a c sub 1, that's going to disappear. Every odd power of x is going to vanish. And remember, c sub 0 we're just going to call 1. So this is going to correspond, the c sub 0's correspond to all of these odd powers, even powers, I am so sorry, of x. By way of comparison, we could also say, now what if c sub 0 was equal to 0 and c sub 1 is equal to 1? Well, then very quickly we could find that y is equal to, now if c sub 0 is 0, all of the even powers of x are going to be gone, but all of the odd powers are going to be present. And very quickly we can arrive at another series that would work just as well. Of course, if these two series are going to each be solutions, the sum of them we would expect to be solutions as well. So this is how we could go about finding two different solutions, two different series solutions. Of course, adding them together would yield a solution as well. Well, hope things are going well. We're just going to continue to re-index and continue to address when we might even have two distinct series solutions. Best of luck to you.